because let's say it's a homolomo gap problem. What we have learned is that if I'm doing a Kohn-Sham calculation, right, a Kohn-Sham calculation, and I'd like to make this picture again. We do a calculation and we get this top of the valence band and bottom of the conduction band, and when I put an extra electron in, this whole thing shifts. By this delta XC. So the fundamental gap is equal to E gap Kohn-Sham plus this delta XC. I minus A is E gap Kohn-Sham plus delta XC. So as far as Kohn-Sham theory is concerned, E gap Kohn-Sham is always going to be less than the experimental fundamental gap. Alright, that is basic. And we do not know how to calculate this WXC within the Kohn-Sham framework. Let's now just see what happens when you use some other theories. So, band gap. There are the theories. And that then becomes the motivation to improve your functionals also. Let's start with Hartree-Fock. For understanding this, I'm going to write Hartree-Fock equation in a particular way. So what was Hartree-Fock equation? We had minus 1/2 L square plus V external plus V Hartree-Fock plus the exchange term, which is minus integral phi. So this acts on phi I minus phi j star r prime phi j r phi I r prime over r minus r prime d r prime equals epsilon I phi I. That's the Hartree-Fock equation, right? Let's look at this term. And this is summed over J, sigma J parallel to sigma I. Actually, there is sigma also. So this is all sigma. Is that okay? Now, if I look at the exchange potential, this is nothing but summation j, sigma j equals, so no, sigma is the same, so I just write this as phi j star sigma r prime, phi j sigma r phi I r prime over r minus r prime d r prime d1, right? And there are several ways of looking at it. One is, let me just draw this. here, and from here I go to this point. One is by looking at it as a multiplicative potential, and then what I'll do is I'll write this as phi I star, phi j star, sigma r phi j r prime, phi I r prime. This is r prime, this is r, divided by phi I r mod r minus r prime dr prime integral. And since I divided by phi I r, I'll also multiply this by phi I r and write this as a potential, right? V exchange I at r acting on phi I r, where Vxi r is nothing but this integral due to this quantity phi j r prime. I'm being very explicit because I want you to see it each and every term. Phi j r phi I r prime over phi I r mod r minus r prime dr. So I can think of the exchange potential as a potential which is orbital dependent, right? It is depends on I, and then it's multiplicative. Is that okay? The only problem with this is that wherever phi r has a node, phi I r has a node, it goes up. So it's not a well-defined potential. Nonetheless, one can still write this as Vxi r as an integral of, I call this a Fermi hole which is I dependent, r prime over r minus r prime dr prime, where rho x I is that four terms, summation j phi j star r phi j r prime r phi I r prime over phi I. This is like the charge density of the system with I dependent. Each electron has its own hole. But again, it's not a well-defined hole because, wherever there is a node, it will go up. So from here, actually, Slater went further, so I just may as well do that. And he said, let us define a hole, average hole, which is the weighted average of this. So I'll weight it with phi I star r, phi I r, this is the weight of the orbital, divided by sum over phi I r, so that will become r for each sigma. Okay, this is particular sigma. Sum over sigma I times rho xi. And this comes out to be the goal. Derived. So this really comes out to be that two-particle probability that we have derived. Okay? So this is one way of looking at this potential. I'll comment on this a little later. Right now I want to make the point about the fundamental gap in the gap in Hartree-Fock theory. Okay? So I can think of this potential as if it is arising from an orbital dependent Fermi hole, right? And work with it, although there are singularities coming in. The other way I can look at it is I've written Vj sigma r prime star Vj r phi I r prime over r minus r prime dr prime integral, right? This is all sigma. this I can write as integral. Instead of an orbital dependent potential, I'm going to write this as a non-local potential. We exchange r prime, phi I, r prime, dr prime, where the potential now is acting non-locally. It's not a multiplicative potential anymore. And Vx on r prime is equal to summation j sigma for the sigmoid orbital, right? Phi, oh this is phi. Phi j sigma r prime star phi j sigma r over r minus r prime. Is that okay? It's a non-local potential. It is summed over all j occupied. Fine? Now, with this, I can actually tell you why the band gaps in Hartree-Fock theory are going to be much larger than what you expect otherwise. Okay, so let's look at that. Now, if I look at this, so what are we doing? When I'm calculating the operation of V Hartree plus V exchange, I'm just writing it symbolically on phi I, it is summation phi j and summation sigma r prime mod square over r minus r prime minus summation j b x sigma integration phi I r prime dr. Are you with me on this? Right, this is what I'm doing. Operation of VE operator on ith orbital. How do I then calculate the virtual orbital? Let's calculate. So let j be equal to 1 through n. Let n orbitals be occupied, and I'm calculating n plus 1n orbital, which is virtual. Okay, this is unoccupied orbital that I'm calculating. So I'll again write this. How do I write this? Well, this sum is over all occupied orbitals. J equals 1 through n. I'll write this as summation sigma summation j phi j sigma r prime mod square over r minus r prime j equals 1 through n, acting on phi n plus 1 r, right, minus summation j equals 1 through n Vx sigma, like this, phi j sigma star r prime phi j r over r minus r prime acting on phi I r prime. Now it will be acting on n plus 1 dr. Is that okay? Okay, now I'm going to do a trick. If I add the self-interaction of n plus 1n orbital on both sides.
Sir?
Yes.
Who got that?
Huh?
So there was a last time row it's multiplied.
There's a problem?
There's
It's
a
okay.
last term.
You can always correct it. So let me write this as summation sigma summation j equals 1 through n plus 1. Okay? Phi j r star phi j r prime over r minus r prime dr prime, and let me do the same thing here. Minus, I'm doing it for n plus 1th orbital, right? N plus 1th orbital. So what I can do is, if I do it up to n plus 1th orbital, let me just see, this is J star. This last term, J n plus 1 star r prime by n plus 1 r prime over r minus r prime dr prime plus last term, this last term. Okay? And this is acting on phi n plus 1 r. Is that okay? Okay. Now, if you look at this term, minus the last term, summation j equals 1 through. You can absorb this term here. All the terms are exactly the same. You can absorb this term here. And instead I can write this up to n plus 1. Up to n plus 1. See if each term matches.
In this last term, J.
Last term is that one.
In the second, in the middle column, J.
You talk to yourself, you're not talking to me.
So, in the second, in the middle column,
Yes.
J equal to occupied, where I have written.
This is all occupied. Now I'm adding and subtracting the last orbital. And if I do that, I can absorb this term that I added and subtracted. The subtracted term I can absorb here. So this whole thing becomes like this. That is the potential action of Hartree-Fock, Hartree plus exchange term on the n plus 1 virtual orbital. So this is like you're solving n plus 1 electron problem. So even if you are calculating a virtual orbital, which is n plus 1th orbital, you are still doing an n plus 1 electron problem. And that means you are over calculating the Coulomb term, or calculating the repulsion. Is that point clear? Although it's a virtual orbital, although you have not filled an electron in it, but when you're doing it, if you look at the theory, that's what you're doing. You're essentially solving an n plus 1 electron problem. So, if let's go pictorially. So I'm expecting you to kind of see that this term really gets absorbed in that properly. All you have to do is switch one from here to there. Right? Now, if this is epsilon n for nth particle, right? Epsilon n plus 1 for nth particle is the same as epsilon n plus 1 for n plus 1 particle. This is virtual, this is real, but they are the same. Okay, so this gap is going to be over estimated by a large amount, by one, by one. So Hartree-Fock bands, wherever you do calculate, they are always overestimated. In Kohn-Sham, they are underestimated. In Hartree-Fock, they are overestimated because you are doing an n plus 1 problem. Same thing you will see in molecules also. If you are trying to calculate the unoccupied orbital, LUMO, much higher than what you expect optically. Hartree-Fock theory, right? And you usually say this is because you are not taking correlation into account. Well, I mean that's correlation is the currency for everything, but what you're doing is correlation will introduce some screening, and therefore this will come down. Okay, but Hartree-Fock theory by itself has this problem. Okay? So this is, Joyita also answered to the question I asked yesterday. Why Hartree-Fock never works together? We're solving an n+1, real n+1 electron problem. Okay? So, then people suggest that make hybrid functionals. We mix E Hartree-Fock plus E DFT, and you end up having something which gives you the right answer. Okay? So this is one point which is usually not discussed, but you should keep in mind that Hartree-Fock bands are always going to be overly large. So that's Hartree-Fock. Now let's look at some of the theories. Then, within DFT, there are other theories. One of the earliest theories that got the band gaps correct was self-interaction corrected theory. It is known as SIC. And I am doing this because this is related to how modern DFT calculations are done using generalized DFT. So in SIC, what one does is let me motivate SIC first. If you look at a single electron problem, from DFT point of view, so DFT, everything is in the density. The total energy, E rho, will be equal to the kinetic energy plus V external R rho R plus E Hartree plus E exchange correlation. This is the formula given in exact DFT, because there is a universal functional, or there is a kinetic energy functional, there is a exchange correlation function in terms of density. And this, for a single electron for it, is 1/2 integration rho r prime over r minus r prime dr prime. However, I also know in a single electron problem the true energy E, single electron, is equal to pi I minus 1/2 L square pi I plus E external. And therefore, I should have EH rho, single electron, is equal to, put a minus sign here, EXC rho, single electron. You must have whatever exchange correlation function you have. This is an exact property it must satisfy. That if I take a single electron density, it must come out to be exactly equal to minus the half of this. Alright, that should be the exact property of an exchange correlation function. But in real life, it doesn't happen. For example, if you take EXCLDA, this is like the exchange part, which is nothing but some constant Cx, rho raised to 4/3 r here. So for a single electron, it will be rho 1 4/3 r dr Cx is not equal to 1/2 of t rho r minus r. You cannot expect this, otherwise calculating Hartree energy will be very easy. So if it is not, that means an electron in local density approximation interacts with itself. Right, and therefore it will underestimate the exchange correlation. Or overall energy will be more positive. Overall eigenvalues will be more positive. Because the electron ends up repelling itself, which should not happen. So it is seeing the effect of other electrons as well as by itself. Right, so one makes self-interaction correction. So what one does, if I have an EXC LDA, this I know overall is going to have self-interaction. So you take each orbital and calculate self-interaction. So for each orbital, you calculate E Hartree by I according to that formula. Add to it E exchange correlation. This is the minus sign. Add to it E exchange correlation for a single orbital. That's right, rho pi I. For each orbital is going to have this much self-interaction. Sum it up for each orbital and subtract it. This is known as EXC LDA. Local density approximation self-interaction corrected. So let me just pause for a few moments here and see if the idea is clear.
So why are we summing over all the orbitals?
Because in each orbital there is some self-interaction. So I'm subtracting for each orbital. Anything else?
Self-interaction is not about the electron but rather the orbital of the electron.
In a single electron, in each orbital there is a single electron. So either orbital or single electron is the same. Any other question? Okay. So once you make this however depends on not just rho alone, phi I also. So now if you calculate the potential, or if you do the Kohn-Sham, you're going to get an I-dependent potential. How does that happen? Remember how we derived Kohn-Sham? Finally I had said that you're minimizing this kinetic energy with respect to phi I under some conditions, right? Yeah, and the potential came out to be the Kohn-Sham potential. I'll look at it another way. If I minimize the total energy, E rho, which is given as minus phi I half del square phi I plus E external plus E Hartree plus E exchange correlation. I minimize this with respect to phi I. I can always do that. Instead of orbital, I can do this. With the condition that they be normalized. I get the Kohn-Sham equation. First term will give you minus 1/2 del square phi I. Second term, I can take d by d rho by phi I, so I get v external phi I. Third term, I get dh by d rho, which gives me v Hartree, d rho by d phi I star gives me v phi I. plus D exchange correlation phi I equals the Lagrange multiplier. Just like we derived Hartree-Fock, we can derive Kohn-Sham equation also like this. I'm minimizing the energy with respect to variation of orbitals rather than just the density. I'm taking one more step. In exactly the same manner, now if I minimize the energy calculated by NDA sec, if I do d phi I star E rho phi I LDA sec minus delta by delta phi I star from I phi I modulus square minus 1 equals 0. I'm going to get the first term all right. Minus 1 half the rise phi I plus P external phi I plus P Hartree phi I. And the last term, because this has an explicit phi I dependence, I'm going to get a potential V LDA sec, which is going to be I dependent phi I equals so. Is that point clear? Because just like in Hartree-Fock theory, there was an I dependent term. In the exchange, I got an I dependent potential, non-local potential. Here it's local, it is multiplicative. However, it just depends on the orbital, just like Hartree theory. Okay, so this is I'm doing, which is not purely Kohn-Sham. I'm not doing a local potential. I'm doing a potential which is orbital dependent. This is usually referred to as generalized. If I get time at the end, I'll justify this. Why it is doing a generalized potential.
And the word generalized. Why the word generalized?
Why generalized? Because a Kohn-Sham is purely local potential, purely orbital dependent potential. Now, that's why I said I'll justify it later. You can always derive a Kohn-Sham density function scheme where you make the potentials of the functionals orbital dependent. Then you get a Kohn-Sham which is not just one potential, different potential. That's known as generalized. The spirit is Kohn-Sham like within DFT. So
But instead of density or
I'm still calculating the density. My functional has become I dependent now. There is an explicit I dependence on the orbital dependence.
but see we use minimization with respect to orbitals.
Yes.
But
This is more general than doing minimization only with respect to rho.
yes, that's
I'm doing each one. And anyway, because phi is a function of rho, they are also related.
So this SIC, basically we can see that, okay, whatever VXC you are doing, then in reality for a single electron there should not be any.
Yes, so I'm subtracting it first.
So, yeah, so whatever the balance must be subtracted.
Subtract.
And that gives me an extra structure.
That gives me an extra stress. That's all.
So when we are calculating the balance,
Yes.
the wave functions we are using is not exact.
Some phi I which I'll finally calculate self-consistently. What do you mean exact? I'm calculating it self-consistently. I'm assuming there are certain orbitals, this is not doing it. I derive the equation, then I solve it self-consistently.
So would it remove the self-integration completely?
Yes, because I'm doing it forcefully.
That's been done there forcefully.
I'm doing it for no matter what the orbitals are, I'm doing it. Now, the potential also you can guess. EXC, LDSA, I is going to be the LDA potential minus the self-interaction correction for that orbital. So it's going to be rho for that orbital over R minus Ri dr prime minus V XC LDA for that single quantum orbital. cancellation is being done itself.
So there is an extra iteration loop. There is an extra iteration loop for
No, iteration, yeah, there is an extra, you do it for each orbital.
each other.
So you're calculating Vx for each orbital separately. That's the extra effort. Yes.
So can we say now that we have solved this main word problem exactly?
No.
Catch?
No. No.
There must be something.
You're still not, because you're still, your to start with your EXC is approximate. If it is not approximate, you would not have any self-interaction. And then you are making self-interaction correction also using that approximate functional. So you may come close, but you're not solving exactly.
So I have removed the error corresponding to the approximate.
That's right, that's right. But I'm still calculating the whole thing approximately. Right? Okay. Now, why I talked about it is, when you do self-interaction and correction, band gaps come out of the orbit. So in set theory, and LD is sick, or any other theory that's sick, band gaps are close. For most of the materials, when we say close, we mean majority of materials to experiments. Better than LDA. Okay? Now, just like giving the interpretation that Hartree-Fock theory gap should be very large, why should it be better the same? Let's understand that. And this is something which not many people talk about. I mean, sick giving error gaps. Why? If we understand such kind of things, maybe we can make things better. Okay, so I'm going to give the argument the way I think about it. Alright? The way I think about it is like this. You're doing band calculation, there is a valence band, the conduction band, and this gap, even if I'm doing LDA, E gap LDA is much smaller than E.
One quick question.
Yes.
Just to understand the discontinuity that we discussed last class, so that came because of force fitting or localization.
Yes.
Now, within this way of Hartree-Fock plus this self-correction, it seems to give reasonably good bandwidth. So is there,
Yeah, so if you calculate that E versus rho N,
yeah,
it just come out to the straight line.
okay,
very close.
So this SIC somehow
Somehow.
relates to this exchange.
Yeah. Okay. Now, the way I look at it is,
Sir, as you already told us that the people are using hybrid functionals to get the better results for the bandwidth. So this functional LDA with the SC self-interaction correction can also be used, no?
this was the first calculation which gave a good band gap in DFT. It's a very famous paper by Purdue and Sunga. You can just note it down. Okay.
So what about the computation cost? When we are
Computation cost obviously is going to go up a bit because now you're calculating orbital field for each potential for each orbital separately.
So it will be more than the
LDA.
functionals also?
It will be more than the local functional, yes.
Local, fine, obviously it will be more than local functional, but is it more than the hybrid also? So that
No, it will be slightly less than hybrid because in hybrid you do a non-local calculation.
yes, there is a more.
That non-local is slightly more. You have an integration step. Here you don't have an integration step.
So it's better to use this one rather than the hybrid.
I don't know comment on that because I don't do any of these.
In hybrid also you do self-interaction. This is one electron, there is many electron self-interaction also. So you have not checked that. So hybrid also you do. So in the hybrid you have that density functional part. There you do. So the Hartree-Fock part is there. That is already taken care. And the other part you have to take care. That is already done. This is nothing, something separate. So this self-interaction correction, it depends on you. So whether you want
Where you want to do it, in what
you
form?
want to do or you don't want to.
No, I think what she's asking is why this is not popular.
No, this is popular.
Popular people do say.
I mean, but as compared to hybrids and things like that.
Because actually you're doing Hartree-Fock also.
Yes.
And this thing is only you're stuck. This is sick, that's it. The other functionals give you more flexibility in terms of tunability, in terms of fixing parameters.
But the DXC is still like one can take LPA or
Whatever approximation is whatever approximation. You calculate some interaction, correct that. That's all.
no, what you are saying is that Hartree-Fock part has its own inbuilt interaction correction.
But if you're taking only part of Hartree-Fock,
Yes.
there is still self-interaction.
There will be then, but the rest of it needs to be corrected.
Yes.
No, it's a hybrid, whatever we are talking. So we are not knowing. So there is already inbuilt, this SIC is already there.
Which way?
In this, in the DFT part. It's already there. And some code they already have this SIC implemented.
But his choice is yours, whether you put that button on or you don't put that button on, right?
Some functionals is already inbuilt.
Okay. It is inbuilt, but it need not be.
It can be the deep suggested is not there.
No, but this cannot be a functional inbuilt thing. This has to be
No,
a
no.
extra complication.
No, in the program you can
Program.
Yes, the program, not in the function.
No,
in the program.
Program.
Yeah, the program you can do it for.
Yeah, so it's that button, that extra button, extra flag.
Yes, yes.
So that's the computation part, but I'm more focused on this thing, right? So now the question is why? And
You can also say something like Fermi MRD.
huh?
Fermi MRD.
Yeah, Fermi MRD comes in the Thomas Fermi, so
So that is also.
yeah. So I mean, yeah, since yesterday he said he should give historical things also. This initially started with correction to Thomas Fermi by Fermi MRD. This was done in 1930s, and the same idea was taken over to the LDA by Purdy and so on. In fact, their first and second reference is Fermi MRD. Okay, now the question is why better? So the way I look at it is, if I look at self-interaction correction, right? So let's consider orbitals which are localized and ones which are delocalized compared to this, right? So this is localized in space and delocalized. Which one do you think has more self-interaction, more Coulombic potential? Localized. So this is larger self-interaction compared to this. Now let's look at the LDA band gap, right? And here is the LDA band gap. The conduction band orbitals are going to be more delocalized compared to the valence band orbitals. Do we agree with that? The higher energy, right? And therefore, if I make self-interaction correction, this is going to go down more than this. Okay? I'll give you better than. This is the way I think about it, and I'll therefore appreciate if you have any comments. Just like in Hartree-Fock, you're doing n+1 problem. Here the correction you are making will be more for localized orbitals, and therefore valence band eigenvalue will get corrected more than the eigenvalue for the conduction band, and therefore the gap will increase.
Could you please repeat it?
If you agree that self-interaction is more in this compared to this, when I make the correction, it's most likely that it will be more for localized orbitals compared to delocalized orbitals. For example, if I have a plane wave, self-interaction is nearly zero. Whereas if it is localized, it will be quite long. Right? So, the correction in the conduction band would be less than the correction in the valence band. Therefore, the gap increases.
Conduction band is anupakat,
You tell me.
is anupakat.
Yes.
So when you are,
It's higher energy, so more very localized.
so when you give the constant iterations,
Yes.
you will take the anupakat.
Yeah, you can always, you have a local potential, you can always calculate it. If I give you a local potential, I can always calculate the occupied gas. What does it matter?
Conduction band is more or delocalized than direct.
What?
Conduction band is more delocalized.
Yes,
than direct.
yes, that's the point. If I give you a local potential, you can always calculate the higher levels. Nobody stops you from doing that. Right now, so this is as far as I'm spending so much time because when you do GGA, meta GGA, in fact meta GGA, the potential VXC comes out to be I dependent. And this gives you metal band gaps compared to if I localize it, somehow I can make a local potential out of it. Local. And there are tricks of doing it. Meta GGA potential. And the way I look at it again is that if the potential somehow, because it's I dependent, affects the conduction band much less than it does the valence band, you are going to get better gaps. That's because, and meta GGA, GGA, all these things, they have gradient of density built in. And gradient would affect valence band much more than it does the conduction band. And therefore correction in valence band is important. Okay, and since it is always the NLD and all these potentials have self-interaction, they are overestimating, so they go down. So valence band will go down more than the conduction band always. Whenever you have an I-dependent potential, you have a chance of getting better band gaps.
There's a chance because they can work, but if there is something like a d orbital up there and a p orbital here.
Yeah, then those are nitty-gritty. But I'm just making a general statement. This is what the expectation will be. Now you can always go d orbitals which are ideally localized. Then it's a different story.
Sir, in later GGA, the potential becomes I-dependent due to the introduction of the order.
Mod phi I, grad phi I square. Right? Okay. So this is what is seen here. And this is my argument. I'm giving this argument because one is trying to understand this physically. I'm trying to understand physically why Hartree-Fock gaps are larger, why SIG gaps should become better, right? So you can always, I mean, you see in the literature the argument given this is correct, minus 1 over R behavior, this. But I think this is the crux. How the orbitals are getting affected. How much time do I have? So any questions on that? I'm going over it very slowly because these are new things, these are things where all DFT people still struggle with and they have to be discussed quite a lot. What I'm saying is maybe not be the last word, but this is how I'm thinking about it. And
So your argument is based on the magnitude of self-interaction as we see.
that's for SIC.
Yeah, I mean, in terms of how we see the Coulomb integrals.
Yes. But for meta GGA is based on where the correction is going to be more. In SIG also I'm looking at the correction. Meta GGA also I'm looking at the correction. There is quite a mystery that you take meta GGA, you take an I-dependent potential, the moment you make it local, the delta XC starts becoming important.
There are ways. So what you can do, you can come up with a very good formula, and then you can. So there are these fractionals are being taken from other ways. So there is this localization, delocalization error. From that angle, you can also.
So the moment you talk about localizing delocalization, this pretty much the same argument.
See, yeah, I mean, basically when you are actually correcting by putting a hole, you are actually saying that there is a screening you have missed. And that self-interaction correction partly probably corrects for the screening.
Yeah.
That also can lower the.
Yeah, that's what it does. It's always lower.
It's always worse.
It lowers the level, but it increases the bandgap.
Yes. See, that lowering you can always interpret as a whole, the presence of some effective hole.
So this is one approach to bandgap. There has been another approach, and so another approach to bandgap problem, in which the group out here, Samuel's group has also done quite a bit, is modeling the potential itself. Okay, and the argument is that if you somehow make, he said this derivative discontinuity, which was finally related to potential being minus 1 over r going to 0 to minus 1 over r. If you relate all this, somehow if you make the potential go correctly in the tail region or low density region, you will get a better gap. So, there is something called the Van Leeuwen finite correction. There is something called the modified Becky-Johnson potential, and third, what should I say? Sound modified Becky-Johnson? So there, I mean, the I suppose. I should say sound. Why not? Okay? Now the idea is again make the potential somehow mimic the delta XC derivative jump or the correct asymptotic behavior or something or the other. So for example, Van Leeuwen's potential is you take V XC and dA and make a correction to it brute force so that it goes as minus 1 over r for larger systems, and that is some functional, right? Some x is to some 1/3, or that there is a sine hyperbolic inverse out here, some beta which is fitted, or something like that. Okay? The bottom line is that this gives us minus 1 over r far away. It gives you better gaps. Modified Becky-Johnson is based on, again, those modeling the exchange hole in a certain way, which was done by Becky and Russell. And then they came up with the Becky-Johnson formula, and this was modified by Peter Blaha. And what is the other name? T, something with T. Tran Blaha. Okay? And this gave good gaps. And what do we call your functional? I will write it. Give me a name. Let's give it a name. Huh? Isn't that a good name? Nice one. good gaps. Okay? Now, so I want to make a comment on this, and particularly in light of there is a paper on archive, very recent paper on archive, and this is going to come out in PRB soon. Okay? What they did, they took Monte Carlo densities for solids. Two solids, silicon and sodium chloride, and inverted them. So these are supposedly exact densities which have been inverted, and the gaps found are smaller than E2. So this is the first time they have shown that if you take real density of a system and calculate the true Kohn-Sham corresponding to that system, gaps come out to be small. And when they compared these densities, particularly modified Becky-Johnson densities, with UMC densities, okay, and found that the two are very different. Different, yes. So you can take a functional, get a good gap, but if you get a good gap, the densities are becoming back. If you take the true density, Monte Carlo is a very accurate density, but it has been done only for these two systems. Gaps not are small. So this, I think, is going to start a new study in the direction of how to balance the band gap and density. I mean, this is as latest as I can come to band gap.
So you said that design density driven function.
Huh?
Density driven function.
This is what is it? Yours is a band gap driven function.
So what we do, they will model the extend parameter using some technique.
Yes.
Now,
So that the gaps come out to be organic. Yeah.
okay, now you do something which will mimic the this quantum Monte Carlo density.
Yeah. So but then the gaps will come out to be. So this is going to start a new study. That's what. So this is where I'll stop. Okay. Thank you.